A sequence is defined as a function whose domain is the set of positive integers. Now we know what functions are just because we've dealt with functions all throughout our algebra classes and through our pre-calc classes and for some time now, but normally when we think about a function we think of something like f of x. Now one thing we probably never thought about was the fact that this x has always been a real number. So in other words, you could plug in something on the real number line, and let's say, for instance, you got x squared. And even when you draw the graph of x squared, we probably never thought about this either, but the graph of x squared is continuous, it's dense. There's no breaks in it because the real number line is dense. You can think of any two x values on the number line, there will always be another one in between them. And between those two, there's something between those, and so on and so forth. So you just get millions and millions of x values on this real number line. But our sequences, on the other hand, are going to be functions, but they're going to be defined only on the set of positive integers. So to denote this difference, probably the easiest way to do it is just to change a letter so there's no confusion. Rather than saying f of x, we'll say f of n. And so you'll see the letter n show up a lot in this chapter. Now, it doesn't have to be an n. Oftentimes we'll switch and we use letters I or J or K, but more often than not we use the letter n. Also, to kind of help eliminate this confusion with the connection to functions of this other type on the continuous domain, we'll rewrite our notation for this function on the positive integers as a sub n most often. So once you get into the chapter, you hardly even think of it as a function of n anymore, but we have to remember that it is. So typically we'll write a sub n. Now what does this a sub n mean? Well, as the n changes or ranges over all the positive integers, 1, 2, 3, etc., you get individual terms. And so instead of having a fluid graph, the graph, if you were going to graph it, would look something like this: 1, 2, 3, 4, 5, etc. You would only have y values at the integer spots. So at 1, a of 1 or a sub 1, sub sub is in subscript 1, you'd have a y value there, and then you'd have a y value at 2, that's a sub 2, and then a sub 3, and then a sub 4, etc. So instead of being on a continuous domain as we're accustomed to, this will be almost called a discrete domain. It's just the set of positive integers here. A bit of vocabulary: we call whatever the term is when n is a particular value, we call it the nth term. The nth term. A beginner question, one of the easier questions that you'll typically be asked, is to generate a certain amount of terms in a sequence. So for instance, if this is your function of n, a sub n equals -1 to the n over n squared, then we can spit out a list of terms however long that they ask us for. So for instance, when n is 1, then let's compute that: -1 to the first over 1 squared, that'd be -1. And then when n is 2, you have -1 squared over 2 squared, so you get a fourth, and then looks like you get -1 ninth, and then +1 16th, and -1 over 25, etc. Now notice for sequences, this is just a list of terms, a list of individual terms. I'm not saying this graph relates to these numbers, but you get the connection I'm trying to make here. Is they're separated by commas. You don't add these terms up or anything like that. It's just a list, just a list of terms that in this case happens to be alternating signs. Now, one of the big questions we often ask about sequences is, does your sequence converge? Converge is a big word in this chapter, and here's the definition. We say that a sequence converges if the limit as n approaches infinity of that sequence equals some limit. So in other words, if these terms level off somewhere like these happen to be converging towards 0, I imagine, because they look like they're getting smaller. Yes, they're changing sign, but it looks like a fourth, a ninth, a 16th, a 25th, a 1 over 64, etc., etc. It looks like this sequence right here, which doesn't relate to that particular graph, but this sequence right here converges to 0. So if that winds up being some limit that's a finite number, then we say that it converges. If it doesn't, then we say that it diverges. So that's your two options. So let's see if this sequence here, I tried to make this one a little more difficult. Let's see if this converges. So we take the limit as n approaches infinity of n plus 1 to the nth power over n to the nth power. So I immediately don't really have any great idea as to whether it converges or not. There's nothing really jumps out except for the fact that this is raised to the nth power and so is this. So maybe we could combine those into a single expression. Limit as n goes to infinity of n plus 1 over n to the nth power. Now just to save a little space, n plus 1 over n, this could actually be reduced down as well. As a matter of fact, I'm just going to do it right here. N over n is 1 plus 1 over n. So I think that would reduce to 1 plus 1 over n. Now I hope that you saw this in pre-cal. Your pre-cal teacher, pre-cal instructor should have made you aware of this. This is a well-known limit. Hopefully we just know that that's the definition of the number e, which is approximately 2.718, etc. So like I said, this one may have been a little bit more on the difficult side, but this one does converge. It converges to about 2.718. So this is a converging sequence or a convergent sequence, where others may not be. Matter of fact, if you look back up at this original example, if we took the sequence, I guess the analogous sequence for this continuous function, a sub n equals n squared, well, notice that just continues to grow and grow and grow larger and larger the bigger n gets. So this sequence would diverge, in case that's hidden behind my pip, picture-in-picture. Let me scroll up. Yeah, a sub n equals n squared, that would diverge, obviously, because the terms just get larger and larger. All right, now here's another popular question that's asked a lot. They will ask for you to find the pattern of a sequence that they provide for you. Now, I've taught this class a long time, so I kind of know the terms you can usually expect to see. Usually is somebody in this list. These are terms that are often used. This little guy right here, minus 1 to the n, his job is to change the sequence terms from positive when n is a even number, like -1 squared, to a negative whenever n is odd. So n obviously changes from an even number to an odd number back to an even number, which will make that expression -1, +1, -1, +1, -1, +1. We oftentimes see n squared or n cubed show up. We oftentimes see powers of 2 or powers of 3 or powers of 5, powers of certain numbers. We all the time see factorials. And just a quick definition in case you don't know what a factorial is. A number like 5 factorial would be defined as 5 times the number below it. So I'll say n minus 1, but that would be like 4 times n minus 2, the number before that like 3, times 2 times 1. So you just keep that pattern no matter what the factorial is down until you get to 1 and then you stop. So 100 factorial would be 100 times 99 times 98, so on and so forth, times 5 times 4 times 3 times 2 times 1. So they can obviously get really big. I would even probably familiarize myself with the first few factorials just so you can recognize them immediately when you see them in a list. Last one, just simply multiples of n, 2n, 3n, 5n, 7n, 9n, 10n, things like that. So here's an example. We'll just try it. I don't think this one is overly difficult or anything. You just look for key indicators in the sequence, especially out of this list I provided. The numerator should be immediately clear. 1, -1, 1, -1, 1, -1. So this will be something with one of these -1 to the ends. Now there's something, and maybe you spotted this already, that I'm going to have to tweak about this, but I'll come back to that in a minute. But it kind of looks like -1 to the end. Now when you look at the denominator, this one's a little more difficult. 2, 5, 10, 17, 26. That doesn't really look like anything. So a common trick is try shifting all those numbers either down 1 or up 1 or down 2 or up 2 to make it get on track to one of these terms that's listed over here. So for instance, if we go up 1, 3, 6, 11, 18, 27, I still don't recognize anything. Let me try going down 1. 1, 4, 9, 16, 25. Oh, that jumps out to me. That's n squared. 1, 4, 9, 16, 25. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So that's a very common technique that we use. So what is ours exactly? Well, it's n squared plus 1. So these take a lot of practice to get really proficient at, but the more you practice, the better you'll get. So anyway, that's just one example of how to find a pattern there. All right, I'm not going to include it in this video because I don't want to get too long, but in the next video you should watch how to compute partial sums or series. And what we're going to be doing in this video is taking these terms in your sequence, and notice we just have commas. Like I said, this is just a list of terms. But next we're going to ask what would happen if you added the first 2 terms, the first 3 terms, the first 5 terms, all the terms of these particular sequences. And that's either known as a partial sum if you just add a few of the terms of a sequence, or it could be called an infinite series if you add up all the terms in a sequence.